Aging is the single greatest risk factor for morbidity or disease and mortality. It dictates the prevalence of nearly every major chronic disease. Yet for much of history, it was considered an inevitable, immutable process. Today, we understand that aging can be quantified, accelerated, and even slowed down. Some aspects can even be reversed, but not all, and certainly not in a way that equates to full body rejuvenation. Yet in a world where longevity research is increasingly commercialized and influencers try to hop on the trend, misinformation and overstatement abound. What is actually possible today? What remains speculative? And how do we distinguish serious biogerontology from well-marketed consumer hype? Today, we will define aging rigorously, examine what we can and cannot do about it right now, and conclude with a framework for evaluating longevity claims in an era of rapidly advancing science. Aging seems simple at first glance, a progressive decline leading to increased mortality, but defining when it begins and how it should be measured is a matter of ongoing debate in scientific and medical circles. Biogerontologists argue that aging is an accumulation of molecular and cellular damage driven by hallmarks of aging such as mitochondrial dysfunction, genomic instability, and epigenetic alterations. In this framework, the decline of physiological function is a secondary consequence of fundamental biological deterioration that starts at the molecular level. Recent studies suggest that epigenetic alterations may play a causative role in aging, with interventions that modify epigenetic markers showing promise in reversing aspects of biological aging. Medical professionals view aging pragmatically as the gradual functional decline that begins around age 30 when peak physiological capacity starts decreasing. This decline is often associated with reductions in VO2 max, decreasing metabolic flexibility, and the onset of sarcopenia or muscle loss. The decline in neurocognitive function, though more subtle, also begins in this window, with studies showing reductions in processing speed, working memory, and executive function. Some researchers, such as Harvard researcher Dr. Vadim Gladyshev, propose that aging starts much earlier as the blastocyte stage, a controversial view suggesting that cellular aging begins immediately after embryonic development resets the aging clock. This hypothesis is based on the observation that early embryonic cells exhibit a transient reduction in biological age before resuming an aging trajectory. If this is true, this would mean that interventions targeting aging may need to be implemented far earlier than we currently believe. Despite these different perspectives, one point remains consistent. Aging results in a statistically predictable increase in morbidity and mortality. Measuring these probabilities remains one of the best ways to define and quantify aging in human population. Additionally, aging research uses biomarkers, specific measurable indicators of aging at the molecular or systemic level. These include epigenetic clocks such as Grimage and Dunedin pace, which estimate biological age by assessing DNA methylation patterns. This is currently the most powerful, accurate, and precise tool we have for measuring biological aging and the effectiveness of interventions in humans. We also have inflammatory markers such as interleukin-6 and C-reactive protein, which correlate with immune aging and systemic disease risk. We have metabolic biomarkers such as insulin sensitivity and mitochondrial efficiency, which decline with age and are associated with longevity outcomes. And then we have functional biomarkers such as grip strength, leg strength, walking speed, and VO2 max, which are correlated with biological age and predict longevity outcomes. Understanding how we define aging is critical because it shapes how we study and intervene in the aging process. If we define aging purely as functional decline, then exercise and lifestyle interventions could be considered anti-aging. However, if aging is defined at a cellular level, then reversing molecular damage becomes the gold standard for intervention. So can aging be reversed? What we know today is if we accept that aging is a process of functional decline, then the real question becomes, can that decline be reversed? What has been reversed in humans? The TRIM trial, a study executed by my colleagues in 2019, demonstrated that the thymus, an organ essential for immune function that literally almost disappears by our 60s, can be partially regenerated in humans. 9 older men showed improved immune markers and, strikingly, a reduction in biological age as measured by multiple epigenetic clocks like the Grimage clock after being administered the cocktail that they used in the study. High-intensity exercise protocols have been shown to rejuvenate mitochondrial function and improve gene gene expression patterns in muscle tissue, making aged muscle more metabolically similar to that of a younger person. Stem cells, known as hematopoietic stem cells, their rejuvenation has been observed in some studies using pharmacological agents like the prescription drug rapamycin and metformin that show promise in restoring youthful immune function in aged people. These findings show that certain tissues and functions can be restored to a much more youthful state. However, there are critical limitations. Structural changes such as facial, skeletal remodeling, and loss of cartilage in joints remain irreversible without surgical interventions. No matter how young somebody finds that they are biologically from these clocks, somehow they never look quite as young, myself included. I'm nearly 41 years old, and I certainly don't look like I'm in my late 20s that I am biologically speaking from these clocks. Neurodegeneration and neuronal loss are also not currently reversible at scale, despite promising animal studies involving cellular reprogramming techniques. Advanced cross-linking in long-lived proteins like collagen stiffening in our arteries has no proven reversal therapy, meaning age-related arterial stiffness remains a major challenge in cardiovascular aging. So while partial rejuvenation has been documented, whole body age reversal remains out of reach. What is scientifically grounded in targeted rejuvenation of specific organ systems. While full reversal remains speculative, there's definitive proof that we can alter the speed of aging. This has been demonstrated in twin studies showing lifestyle-driven differences in epigenetic age, where identical twins with differing health behaviors show distinct biological ages. The Dunedin PACE study, which quantified the variation in aging rates across individuals, found that some aged 40% slower biologically than average, while others aged more than 1.2 years per year. The calorie trial, a study found that a 25% reduction in caloric intake in humans was able to slow biological aging markers by approximately 2 to 3% over 2 years. Pharmacological interventions such as low-dose rapamycin have shown promise in delaying biological aging markers in human trials. Senolytics are a class of drugs that selectively clear senescent cells, these zombie cells that accumulate as we age, and they've shown potential in delaying age-related dysfunction in animal studies and in early-stage human trials. All of these studies reinforce that environmental factors play a dominant role in aging compared to genetics. The good news is that this means aging is not entirely predetermined. So to summarize, aging is measurable, and it can be quantified through morbidity or disease risk and mortality or death risk, and things like epigenetic biological aging clocks. It's possible to slow down the aging process through interventions validated in human trials. Partial rejuvenation has been demonstrated in specific systems like the thymus, muscle function, and in immune cells, but whole body age reversal remains speculative. Distinguishing legitimate science from hype requires skepticism towards therapies that have not been tested in well-controlled scientific studies. The most effective interventions available today are behavioral. For example, exercise, nutrition, and stress management, to name a few, with pharmacological approaches still in early stages of validation. Future directions include cellular reprogramming, senolytics, and tissue engineering, all of which hold promise, but are not yet clinically validated for systemic whole body age reversal. The future of longevity research is promising, but today we must base our conclusions on proven science, not speculation. Knowing the difference between what is currently possible and what is theoretically possible allows us to make informed decisions, whether as researchers, clinicians, or individuals pursuing longer, healthier lives. So make sure to subscribe, comment, and like this video if you'd like to be kept informed on the latest top-grade scientific discoveries in the field of aging and what you can do in your life to slow the process down. And make sure to follow on Instagram, X, TikTok, YouTube, LinkedIn, and send me questions if you have any, because I love to answer them and dig in on the topics that you care about most.